This section talks about inverse functions. And inverse functions, the big idea that we want to have for this is that whenever you have an x value, you're going to swap it with the y value. That's our big idea here. Swapping x and y values, or swapping domain and range values. So if you ever have a set of ordered pairs, something like a table value down here, all you need to do is switch them. When you actually have a function, it's a little different, but it's the same idea, swapping x and y. So a couple of things that we're going to notice as we go through here is that x and y values swap, which means domain and range switch. So that's these two. Once you do that, you may not be guaranteed a function. You might have started with something that is a function as a relation. Remember, each x goes to one individual unique y, but the inverse might not be a function, so we have to watch out for that. We are going to see that the graph is reflected about the line y equals x, the diagonal line, and we can verify if two things are inverses by composing them, which is what we saw in section 1.5. And if we end up with the identity, then we have it. So we're going to take a look at these things. First of all, if we have a set of ordered values, this is where he said you just swap the x's and the y. So if this is x, this is f of x, then we'll say the new x and the new f of x here, inverse, original. We say these swap, so that's 245. And you've seen something like this in college algebra or algebra 2, where they simply flip-flop. Also, we have different notation for inverses. We can say this is an inverse. Whether or not we're allowed to put an x after it depends on whether or not it's a function. We'll talk a little bit more about that later. But if you ever see that little -1 up top with a superscript, that means inverse. That's finding the inverse of ordered pairs or a table of values. What do you do when it's actually a function? It's the same idea. You're still going to take the x and the y's and swap them. What does that mean for us here? Well, where's the y in a function? That's the output. So y equals 4x is equivalent to f of x equals 4x minus 1. To swap x and y, we'll say x equals 4y minus 1. So they just switched. This is now an inverse. It's still an original at this point. It's an inverse at this stage. Then we solve for y. We're not used to looking at things in terms of x, so we solve for y. We'll move the 1 over. X plus 1 equals 4y. So we'll have 1/4 x plus 1/4 equals y, or you could also say x plus 1 over 4 equals y. Either one of those work. But these then are your inverse. We don't know if they're necessarily a function or not yet, but we know it's the inverse of this function, the original. Verify that the two are inverses, and it says here the two functions are inverses. If you're going to look at either one of these equations, they're the same thing. If you look at this inverse on a graph, you're looking to see does it pass a vertical line test. And sure enough, we can see that when we put this into a calculator, it will pass our vertical line test. This just has a slope on our x, and this just has a y-intercept. So it's just going to be a straight line, just like this one. It's going to have a slope and an intercept. To verify that two functions are inverses, you need to take f of f inverse of x, and you must also do the reverse, f inverse of f of x. If both of those give you the identity, which would be x in this case, then you know that they are inverses of each other. So, to verify our first way here, these ones y's over here, remember I said you could put the little f inverse sign? We could also write this. We could say x plus 1 over 4 equals f inverse. So, when we say f of f inverse of x, remember that means outer and inner functions. It's the same as saying f of little f inverse there. It's the same thing. So what's our big pattern? Our big pattern is 4 times something minus 1. Into that something, we're going to put the inverse here, x plus 1 over 4. So 4 over 4 here, those are going to cancel. We'll have x plus 1 minus 1 cancels. We end up with x. So that's our first one. We also need to check the second, which is this way, f inverse of f. So what's the pattern here? The pattern here is something up top over 4. Into that something up top, we'll put 4x minus 1. The minus 1's cancel, so we have 4x over 4. 4's cancel, we end up with x. So, yes, these two functions are inverses of each other. So that's for our first example here. They're inverses of each other. For our second example, we're going to do the exact same process. This is the original. We say y equals 8x. To get the inverse, we'll say x equals 8y. Solve for this. X over 8 equals y, or x over 8 equals f inverse. Okay. Again, it becomes an inverse as soon as you swap the x and the y. So this is still an original, this is the inverse here. To check it, to verify, the outer function comes first, the f, so 8 of something. We put in the x over 8, the inverse, cancels, we get x. And then to do the reverse, we say something over 8, and into that something over 8 we'll put the function. Both functions are inverses. So a lot of things to remember with that, but it uses your skill from 1.5. To continue this section here in your next page, this one simply asks us to verify if these two functions are inverses. You might see this in a homework or on a quiz or a test. If you're ever asked to verify about inverses, think composition. You want to compose them together. Remember, you have to compose both ways to check it. So if we call this f and this f inverse, start our first one. F of f inverse would give you 7 of something plus 4. Into that something we'll put x minus 7 over 4. These are not going to cancel here. This is going to give you 7x minus 49 all over 4 plus 4. Not canceling. So we say no, not inverses, because we didn't end up with the identity. Remember, the identity is x. And that's all we have to put for that. Okay. So, to discover whether or not things are functions, I mentioned that briefly before, we have to make sure that it passes, a graphing test if we're looking at it. Well, there's another way you can do it too. We say that something that is a function and its inverse is also a function means that something is one-to-one. Remember when we talk about mapping things, we say, okay, here's our domain, here's our range, every x is paired with only one y. Well, if this is true, if we can go backwards and that same relation holds true, it's one-to-one. Remember that it was okay to have two things that shared the same range, right? Two people can have the same birthday. Well, think about having another element in here that shares one of these ranges. If you were to reverse that, because remember when you swap domain and range here for an inverse function, and you were to suddenly have things going this way, that would not be a function with that third line there. So we don't want that third line. You want to just be one-to-one. Every element in the domain is paired with exactly one element in the range. This means that not only will your function be a function, obviously, but your inverse will also be a function. Another way to test this, to test if something is one-to-one, is to do what we call a horizontal line test. You've seen before the vertical line test where you go this way. If it passes the vertical line test, it's a function. But if it also passes a horizontal line test, you know the inverse will be a function right here. That's our key. So, using a graphing utility, let's talk about the inverses of these. This is our function. We actually have to find the inverse for it first. So our inverse here, remember this is still the original at this point. I have the inverse as soon as I swap my x and y values. And then solve for y. To undo a cubed, I'm going to do a cubed root. So cubed root x plus 2 equals y. This is my inverse. Now, I want to go ahead and see if this actually passes the vertical line test for itself here. So in my y equals, does this function pass a vertical line test? Math. Okay, so this one passes a vertical line test. So this is a function here. We're going to call this f inverse of x. I could actually have told you from this one that this was going to be a function. So I didn't have to check this one if I looked at the graph for this one. So let's look at our graph for the original one up top here. Let's say x cubed minus 2. That's our graph for that. Just do a quick sketch over here. Okay. So this one is a function. It passes my vertical line test, no question there. However, this original one also passes a horizontal line test. Nowhere does my pen hit this graph more than once as I move horizontally. That tells me, passing this vertical line test here, horizontal line test here, that my inverse will be a function. And again, if you remember thinking about, here's my original, and here's the inverse. Let's go ahead and let's make that one bold so you can see it. Okay. Doing a horizontal on my original is exactly the same as doing a vertical on the inverse. Do you see that? Without moving my pen, the horizontal on the original thin line is the same as a vertical on the inverse bold line. So you can do a horizontal line test on the original to tell you about the inverse. Now, it also says using a graphing utility to verify. When we're verifying with a graphing utility, that doesn't mean that we have to do the composition part. That means we're looking at the two graphs. So if I go ahead and I put this bold one on here, this is my inverse one. What am I looking for to tell that these two are inverses? Well, we are looking to see, do they reflect about that y equals x line, that diagonal line heading through? Because that means that y and x have switched. And that's the idea of an inverse. Y and x switch. So if y and x are the reflection for these two functions, then they are inverses. So yes, these two are. Yes. Reflect about y equals x, therefore inverses. Okay. Let's go ahead and let's look at this last one here. Close up these ideas. Find the inverse function and use a graphing utility to verify. This one's a little different because we've got this negative underneath, and we know that those negatives can cause problems for us. So we want to first think about what's our domain and range of this guy, and then we'll worry about finding inverses. So domain and range, what is allowed to be on the inside and what's not. So plugging in values here, think about what could be in here. We know that negative x squared plus 9 must be positive. It could be equal to 0, but can't be less than 0. So what types of values will make this true? Well, negative x squared greater than or equal to negative 9. Or we could flip-flop this. We could say x squared less than or equal to 9. Taking square roots, x less than or equal to 3. So that's a starting point for us. X less than or equal to 3. So let's think about this. Put in a 3. We'll get 9 in the front. Negative 9 plus 9 is 0. That's okay. Put in a 2. That's 4. So that's still 5. That's okay. Put in a 1. Okay, we're fine there. Going down, going down. What if I put in a positive 4? That'd be negative 16. So that's no good. So it has to be less than or equal to 3. But because it's a squared, we also need to watch out for negatives. Think about negatives 3. Negative 3 would give you a positive 9, but that's opposite. So negative 9 plus 9 again. If I put in a negative 4, that'd be positive 16. Negative 16 plus 9 doesn't work. So I'm restricted. My domain has to be between negative 3 and positive 3. My range, what are the possible things that could come out of this? This is going to have to do with, let's see, what if we put in a positive 3? That would be 9, negative 9 plus 9, 0. If I put in negative 3, same thing, 0. Am I going to get any more than that? Well, for this one here, let's look at a graph to help us. The square root, square root, there we go, of negative x squared plus 9. Okay, interesting, little semicircle. Sure enough, my domain is from 1 to negative 3 to negative 3. My range does start at 0. It goes up to 1, 2, 3. And it includes 0 to 3. I could have written the domain another way as well. I could have also written this as negative 3, comma 3. We want to keep that domain and range in mind as we work with this one. It's the negative underneath here that's making this tricky for us. So we are going to find the inverse, and then we're going to have to think carefully about what the domain and range will be of the inverse. So let's find the inverse algebraically. Y equals square root negative x squared plus 9. Remember that when you take the square root of something, you have to add a plus minus in here. I don't know if it's a function quite yet, so I'm going to hold off on that. But when you take the square root, you have to add a plus minus. We actually want to go ahead and think about the graph of this first before I put a final answer in here. Remember we had this domain and range restriction on the original? That means we're going to have domain and range restrictions on this guy as well. Okay? So if this is domain and range for him, then domain and range down here, this one, flip-flopping this, 0 to 3, and negative 3 to 3. Think about what this is going to look like in a picture then. So this one if we were to go ahead and put this into our calculator, negative x squared plus 9, it's already there, so it matches my original. That's the plus 1. Here's the minus 1. So this is the plus minus. This is the second line right here. If I'm going to graph both of these. Whoa. Sorry, hold up. I forgot my negative here. There we go. Okay, so both of these graphed together as an inverse gives me a circle. That is not a function. If I try my line test on that, that's not working. So we need to choose one or the other. We're going to go ahead, and it doesn't matter which one you choose. You could choose plus or minus. If you chose the plus, you would just get the top half. If you chose the minus, you'd get the bottom half. I'm just going to choose plus because it's easiest. So that's going to do a function for me there. However, if I'm restricted on my domain and range here, that's going to create a little bit of a different picture. So here's what we chose, but I'm restricting myself to 0 to 3 domain-wise, -3 to +3 range-wise. So that means this little piece is my F inverse piece, the F inverse function. That is now a function if I put these restrictions on it. So sometimes when you're looking at the negatives underneath, you can't just do the algebraic. You actually do have to think about what's the domain and the range, and then flip-flop those. Remember, that's the definition of an inverse. You switch y and x, or switch the domain and range here.